Alright, let's get started. Good morning. Seems like a slightly leaner class today. Hope it's not snow. It doesn't seem like that much snow, right? I haven't graded the exam yet. I was hoping to give it today, but I'm still in the process of grading the stuff, right? So hopefully keep that and the homework assignments and stuff on Monday, right? So today we started the next chapter on CPU scheduling. But before we go there, I want us to get a sense of what we've achieved so far. Some of it may have been taught in the, I might have mentioned in the lecture. Some of it is part of your projects and what have you. Right? So what we looked at so far was you have this piece of hardware, and how do you get that started, sort of, to an operating system, and what does kind of you should start, right? We don't know all the data structures that the operating system has, but to begin with, there has to be something. There has to be a firmware or some piece of hardware which will do some kind of a probing to figure out what is in the system to let the operating system know, because the operating system cannot know what hardware there are without itself being running, and for it to run, it needs to know stuff like how many processors there are, how much memory there is, and stuff like that, right? So you need to have this. So when you boot up your machine, you typically see this little screen where it says how much memory you have, kind of thing, right? So those are done by the firmware or something which is part of the hardware, and it creates a list of all the hardware that it detects on the system, right? And it somehow gives a list to the operating system. So operating system, it figures out all the list of hardware, then calls the operating system, right? And operating system, when it starts up, will look at this list, and for each one of the devices there are, it'll try to load a driver, which is sort of the modular operating system notion. So it will load all the drivers needed for talking with all this hardware. So if you build an operating system which does not have a particular driver, then it cannot talk to the particular hardware, then it won't be able to proceed, right? And you may or may not have seen that for your project. So you may find that your new kernel does not do the network because it does not know how to talk to this stuff, right? So once operating system starts all these modules or drivers, it has to set up some data structures internally, right? It has to load itself and set some data structures. The only data structures we have seen is the PCB, which is the process control block. So for every process, we create this notion of a process control block. And as we add more resources like disk and memory and all those things, those are all kept track of by this process control block, right? We didn't say how this is allocated, but traditionally those are statically allocated because the operating system does not want to do a dynamic allocation. It prefers to do static allocation. Can you guess why it would prefer to do a static allocation rather than a dynamic allocation? Dynamic allocation meaning something like a MLR card or some system call like that. Yes? Yeah, it'll take more time. And the other bottom line is, when you are a process and you ask for memory, right? You ask the operating system. But if the operating system wants more memory, it asks itself, right? So why go through a process of itself asking itself for more memory when it's the one it's supposed to know, right? So there is nobody else it has to ask. It has to ask itself to free up some memory, and it does stuff. So there are places where you do this, right? It's not the same as your malloc. If you look at your kernel code, Linux calls it kalloc, right, for kernel allocator, which works different from your malloc in some sense. But for stuff like processors, right, it knows you're going to need processors, so it might as well allocate them statically, right? And for each device driver, it knows what devices there are because that's how it booted up the system. So for each device, it probably have a little queue of how many things you should wait. And you come up with some numbers. So if your system, you kind of figure that if you have a PCB of 1 million, that's way too much. You're never going to be able to manipulate that much. So you create some number which sounds reasonable, which are parameters that you can modify when you build the kernel. So when you look at the kernel make menu config, you can look through the different stuff and you may see stuff like how much process table, how much other entries you can reconfigure. Right? So once you configure that, that's how much is allocated by operating system. Right? And once you have the processes running, they go through different states of wait or waiting for I/O, ready but waiting for CPU, or running state, right? So, next, let's look at the notion of how to schedule this stuff. Before we go there, one of the questions I asked in the exam, right, concerned this figure, which was from, I think, lecture 5, right? So here, if you look at the registers and stack, right, those are thread specific. I mean, the way the diagram shows, each of these threads have this thread and registers, right, to themselves. So even though they are supposed to be for thread specific, they're all part of a single process, right? So whatever process sharing happens will happen here too. That was what I was asking, right? So if you have something on the stack, even though it's supposed to stay within the stuff, you can ask around, because that's how you do in C. You always pass a pointer to some local variable, in which case you're passing the stuff across, right? And before you even go there, on I think lecture 4, we had this notion of what processes are, right? This notion of text and data and heap and stack, right? So these are different areas of your program memory that you keep track differently, you act differently, right? And those are actually created by compilers. How many of you taken a course on compilers? Oh, none of you, right? So if you haven't taken a course in compilers, essentially when you do a compilation of your code, it takes your program and creates into these little segments, right? It does this so it can tell the operating system what it wants, right? So if you build, so stack is traditionally where you put your local variables. If you're using C, the local variables tend to go into the data structure like stack, right? The idea here is every time you call a function, you're kind of pushing the whole global variables into the stack. And so that's traditionally how you build your stack. And heap is traditionally where you do, when you do a malloc call, you get the data from heap, right? Data is where you put all the global variables. So if you, in your C program, if you want to print hello world, that hello world is a string, right? It's a constant string. So that will be stored in data. And text is where you have the program, right? And this way of dealing with stuff is a lot more convenient for the compilers to do. So when you take a compiler course, compilers take your program and put them into this different stuff. And then they, on the header of your program, it tells how much of each it wants, right? It says, I have a program which needs 1,000 bytes of text memory, some amount of data, some amount of what have you, right? So when the operating system loads your program, it looks at those data structures to see how much it needs to give to start your program. Right? So that means the operating system has to know what your program structure is. And if you're used to Linux, they call it ELF format, ELF or A.out format. If you have Windows, there's certain formats. This is the one which prevents, like if you take your Mac program to a Windows program, right, Windows system, right? Windows system does not know how to load this stuff. So even if you are operating on the same hardware, your operating system needs to know how to read your program and allocate these data structures, right? So this, we'll go through more in compilers on how you create this stuff. But for now, you need to know that there are these different areas, right? For our practical purposes, it's the same memory, but the program treats it differently, and that's what we need to know. Right? Does that make sense? So you've been using all these concepts in when you do your C program without perhaps somebody telling you that these go into different areas of memory, right? Right. So whenever I put up a slide and you don't understand what, like stack or data or heap or something, let me know, because I'm not sure where you get that background in the course of action, right? So I hope it's now clear, sort of, somehow magically from a compiler, you have all this stuff. Whenever a process starts, it asks operating system sets the stuff up for you. So your program can start running. And for every program which is running, the operating system keeps track it through a PCB, right? And you have some data queues and stuff, right? And we have this notion of a wait or running or ready processes, right? So now what we're going to look at is how do you schedule a process which is on the ready queue to run on the CPU. So if you have one processor and you have two jobs which are two processes which are ready to run because they're on the ready queue, how do you decide which one to run, which one not to run, right? And that's the notion of scheduling which we'll look at, right? So are things clear so far? So in terms of scheduling, right, the basic assumption is, or basic observation is, processes go through this period of input, output, and processing, right? So they go from a state of waiting and ready, right? Because whenever they do a I/O, they can be put on the wait queue, right? The reason why we do scheduling is we assume that you're going to go through that process. So when you're going to the I/O, when you're requesting I/O, that's a good time for me to give the processor to some other process such that you won't notice, right? If you have to wait for reading something from the keyboard and it takes you, say, 10 seconds, while you're waiting, if I take the processor and give it to somebody else, your process would not notice anything because it was not using the processor, right? This will not work if all you did was just computing something. If your program starts and computes, say, 5 to the nth degree, and it ends, right? It doesn't print anything, right? There, you're asking for a processor all the time. So if I take the processor away from you, you would notice it, right? If you expect the program to run for a minute and take the processor away for a minute from you, now it takes you 2 minutes and you'll notice that, right? And that is traditionally not the case. So the operating systems are optimized for the case where processes go through I/O and computation. So if you look at the like a typical program, it usually does some input/output, operate on the data, write something, read something, operate something, right? And what you need to realize is, if your process does not follow this model, any scheduling heuristics that you develop would not be good for you, right? And again, going back to the answer of anything depends, right? There are no one solution. All the solutions we are trying to do a trade-off. The trade-off depends on some of the observations. So if you wrote a program which does all computation, then this model would mean that your program runs slower and you have to deal with that, right? And so the companies like Microsoft or Apple go through and profile typical applications, right? So they kind of figure what applications people typically run, and they try to see how much of I/O burst you have, how much of a CPU burst you have, and they try to optimize it for that particular user, right? You don't want to build a operating system which is horrible for everyone, right? You assume that it's going to be bad for somebody, right? You're going to find somebody who's doing all CPU computation. You're not going to make them happy. But you want to satisfy the most number of users. So you try to figure out who the most number of users. You try to figure out what they do. So you may either hire them to do the work. You may hire people who do this sort of work. Or you get statistics somehow. And you kind of build this knowledge of a typical Windows user, right? Which you and I may not know who they are. Maybe corporate user or something, right? They tend to use PowerPoint 80% of the time. They tend to, when they're using PowerPoint, they tend to write Word and so on and so forth. So they know the mix of what they tend to do. And you want to optimize operating systems such that that user would be happy. The most number of users would be happy by the decisions you make. And so one such graph may be something like this, right? It shows the amount of time that your CPU, you get a CPU burst before I/O, right? So on the x-axis you have the duration, how much time you want, and the y-axis is the number of times you see the stuff. The graph is sort of like a Zipfian or long-tailed, right? Essentially what it says is most of the processes have a very short CPU burst and a long processing burst, right? So what that means is if I schedule your process to say run for 8 milliseconds in this graph, right? That means, remember this is the project, the one I'm doing for a homework project, right? So if I give each process say 8 milliseconds, that means any CPU burst that you have would be satisfiable within here, right? So if you do 100 hertz, right? So you're doing 1 over 100 seconds, right? So using that, you figure out how much to give, right? So if you give a process, let's say 1 millisecond, right, which is 1 over 1,000, if you do 1,000 hertz, right? 1,000 hertz is 1 millisecond, right? So if you're doing 1,000 hertz or 1 millisecond, you give a process this much time, right? That means if you look at this graph, a typical process needs, let's say this is like a 2 millisecond, right? It needs 2 milliseconds of CPU burst before it does the next processing. So if I give each process 1 millisecond, that means when I get the CPU back, chances are your process won't have finished. Only the processes like till here would have finished, the rest of them won't have finished, right? So you look at graphs like this to figure out how much to give, right? If I give a process of say 100 millisecond, right, that means I'll cover the CPU burst for everybody, but I'm also wasting because it seems like there's so few processes which are using this much of time, right? If you look at the y-axis, let's say this is 5, right? Only 5 times processors have a CPU burst of, let's say, 16 or 24 or 32 or 40, right? So if I look at this graph, I would say something like 8 millisecond or 10 millisecond. 8 milliseconds should be fine, right? If I give 8 millisecond to each process, then each CPU burst that you have would be satisfiable by within the 8 millisecond. So most of the processors would be able to do what they have to do, and all of them is going to go to do I/O anyway. So these processors won't even know that I'm doing the switch because they get to do their computation before the time runs out. Does that make sense? And the challenge is to get this graph, right? The graph clearly is going to be different for different users, different what have you. And in the case of your project, you're just trying in the dark, you're just trying some numbers. Whereas companies like Microsoft or Apple would have to draw these kind of graphs to figure out what's a good number, right? And give that stuff. So if this was the case and I gave 8 milliseconds, all your process would be happy. They won't even know I'm doing this stuff, and we'll be fine. And if I gave 1 millisecond, you will go through so many context switches here for nothing, right? Because most of the processes need more time than that, right? So that's how you come up. So you make scheduling decisions. So some of the numbers of how much clock frequency to use depend on some observed behavior of what you expect these processes to do, right? So what happens? Let's say I have this graph, right? What happens if you increase the processor speed, right? Suppose this was for a 1 gigahertz processor. Now you have a 4 gigahertz processor, right? All things being equals, roughly, sort of, what will happen to this graph? This shows the amount of time that you run on the CPU before you have to give up, right? Now I made their processor go 4 times faster, right? So what would happen to this graph? Yes?
Okay, compress the side.
Yeah, you probably make this like, this will be like 2, right? It's either compressed or this will become 2, this will become 4, and so on, right? So roughly speaking, because this is fully processor bound, and if you assume that doubling the processor frequency doubles the how fast it runs, right? You suspect that this will go from 8 to say 2, right? So here's another reason why. So it's not just understanding this. You also have to understand how that mapping happens, right? So if next time you look at Linux, it'll tell you there's something called BOGO MIPS, right? BOGO-MIPS. If you look at what it's printing when it's booting up, it'll tell you it's running a BOGO MIPS, right? One of the things is it's trying to figure out how fast your machine is, not using these clock frequency things, but it does some little test to see how fast things are, right? So hopefully you can use that to scale this thing back and forth, right? So that way you can build one Linux, and depending on what machine you run, you can potentially make this go on this particular machine, it's 8 milliseconds. On the faster machine, it's 2 milliseconds or what have you, right? So this thing scales with the stuff. So that's part of what the operating system has to do. It has to figure out how fast your machine really is, not just on the clock frequency. So it'll have to run a little CPU test to see how fast it runs, and it scales everything based on that, right? So it's not as trivial. It has to do all the stuff. If it does a good job, you won't notice a thing. If it does a bad job, you'll see a lot more crashing, a lot more interrupts than you wanted to. Right? So essentially at this point, the CPU scheduler has to figure out which process to run from the ready queue. So you expect there are multiple processes on the ready queue. I have to choose one of them to run, right? And I can choose somebody to run either while the process is in any of the states. So I can choose a process to run if the process is waiting on I/O request, right? So if a process is switching from running to wait state, right? So when in the state diagram, when you go from running to wait state, I can decide scheduling. I can decide when to do scheduling, how to do scheduling on the system. If a process is going from waiting state to ready state, I can decide. If a process goes from ready to run state, I can decide. Right? Like I said before, operating systems don't run all the time. They only run when you give control to the operating system. And in this case, whenever there's a state transition, you get to decide what to do. Right? And some of these transitions are preemptive. Some of these things are non-preemptive. Preemptive means that when I do this when I take you off the queue, you don't even notice, right? Because you're voluntarily giving up your slot. So for example, case one is when you're switching from running to wait state. So if you're running in a CPU and suddenly you need to do a I/O, right? So you as a process decide that you need the input output. So you have to tell the operating system, I need to read a byte from the keyboard, right? So at that point, if the operating system takes the CPU away from you, you won't notice because you already gave up, you know you're waiting for the input output. So you're not particularly aware. I mean, you can't do anything with the CPU even if I gave it to you, right? So those are called preemptive because you were voluntarily surrendering the stuff, right? And the case 4 is terminates, right? So if your process, you call the exit. At that point, after you exit, I take a CPU from you. You won't notice because your process is terminating anyway. So you're fine, right? The preemptive case means that you are not asking for it. You're running on the, let's say, the run state. You keep running your program, and I take it away from you, right? The way I do that is I may use the clock interrupt, like what you're doing for a homework project. I create a timer, and when the timer goes off, I get an interrupt. And as operating system, I look at all the processes which are running. I decide that you have used too much of the CPU, so I decide to take the CPU away from you, right? That means you didn't ask for it. You didn't want this to happen, right? Those are preemptive, and you have to make sure that I do this in such a fashion that you don't notice this stuff. Right? So I have to be careful on what you do. Whereas in the case of when you are voluntarily giving up your CPU, taking it away from you is not easier. So I need to make sure that, like when I take it away from you, you are in a good state where you can come back, right? So good state may be that there are some states which are not good, and that may be either because the hardware requires you to do something or the software, right? Hardware may be if you're doing, so if you take a course in architecture, right, you have like pipeline processes and all those things, right? So when you're doing an instruction which requires some things in the hardware going on, I can't just yank it away from you because you may be part way through. So if you're doing a floating point arithmetic, right, your answer may be computed in the process of being returned back, and I can't just take you because then that's a bad thing, right? So for those, I need the hardware support. The hardware has to finish whatever it has to do, roll back, so such that I can do this taking away from you, right? So those are stuff that I need hardware support, and most modern hardware has support where when you do this, when you do the context switch, it'll either finish whatever it's doing, or roll back to the state where it was before it started what it was doing, such that you can restart and you won't notice a thing, right? So if the hardware did not support that, then you're in trouble. So if your older hardware did not support that, you have to deal with that, right? Or if you're using the smaller watch computer or something, you have to keep track of what has to be rolled back and stuff, right? So those are all part of what the operating system has to do to make sure that if it interrupts you, you are in a state such that you can go get back to what you're doing. The point here is if you have to do, like say, instruction 1, 2, 3, 4, 5, right, for your program, while you're working on 3, if I have to do a context switch, I have to make sure that either you are in the state where you've completed 3 or if you're about to do 3. I can't leave it halfway through, because if I restart you, then you may not be able to, so you may be doing 3 over and over again, which is not good, right? Let's say 3 is adding something to an integer. You don't want it to be running twice, in which case your answers will be wrong. So that's one case, right? The other case is you may be waiting for something within the operating system, right? So you may have requested to find out what's the current system time. So when it does an interrupt and your thread is logically inside the kernel doing something, either I have to restart this process or let you finish what you're doing, right? So that when you start running again, you either have the future time or the current time, but not the one in the middle, right? I mean, it's especially problematic if you're operating on some data which is being modified, right? So either cases, I have to make sure that when I interrupt you and then you come back, you don't notice a thing, right? You may notice the time has passed, but not your values and your program should be fine, right? So this only happens when I'm preempting you without your consent. If I'm preempting you with your consent, you won't notice because you're not doing anything anyway, right? Both the case of you doing I/O kinds of stuff, right? And the specific module which does that is the dispatcher. So it's a little piece of code which will have to make sure that if it's trying to switch from one process to another process, it has to make sure that it saves all the state of the previous process, right? And the process may include the state within kernel or what have you. Everything such that when I start you back, you won't notice a thing. So I need to completely freeze one process, completely unthaw one process, which means that I take all the saved state from the PCB, load it into the operating system, the hardware where you want them to be, and then you restart, so that after the dispatcher is finished, when you're running process 1, now you're running process 2. Both of them don't know anything which happened. They start running. Right? So if you want to look at how the dispatcher looks, if you look at the kernel, let's for example Linux, right? If you look at the kernel directory, you can see a dispatcher.s. .s is assembly code, right? It's not run in C, it's written in assembly code, which is a lot closer to a machine language code. You have to do that because these things have to run extremely fast. So these are hand-tuned, specific to a particular machine, and these are supposed to run as fast as possible. It has to manipulate some of the hardware to make sure that everything runs. So you'll have to do this for a machine. So this is sort of like the core of the operating system, right? So you have to get this right. If you get this wrong, your system you won't be able to context switch between processes and everything breaks down, right? And this particular code is in assembly language, which means that for different hardware, you'll have a different code. For Intel, you'll have one code. For PowerPoint, you'll have another code, and so on and so forth. It may be even different between the same stuff. It may be for Intel, Core 2 is one thing, Core 1 is something, right? 32-bit, 64-bit, all those things, right? So this is a very crucial stuff because you want to make sure that once you finish one process to another process is cleanly achieved, right? So those are the big picture of what you have to do. Now we'll look at the metrics of how you would know what is a good schedule, right? If you had only one process to run, the choice is clear, right? If you want to schedule and there's only one process which wants to run, which is on the ready queue, I schedule that and life is simple. But you don't assume that. You assume that there are more than one process. Now you have to figure out which one to run, right? And you may decide to run based on a number of different metrics, and some of the metrics are described here. The first metric is CPU utilization, right? And your goal here is to make sure that the CPU is used all the time, right? You don't care about anything else. You only care about the CPU is used all the time, right? And you want to maximize the stuff. You don't want to minimize the stuff. You want to use the CPU the maximum stuff, right? And this makes sense in cases where the processor is very expensive, right? So suppose you're a mainframe computer and your processor is a few $1 million, right? You have this really big machine where the time to run on the machine, the machine hardware costs you a few $1 million, and you want to make sure that your investment is fully utilized, so you want your CPU to be 100% utilized, right? On the other hand, your processor may be running on your laptop or whatever. Here you may not care about using the processor all the time because the human time becomes valuable, right? If you have a $500 desktop and you as a user have to, because of the high utilization, have to make you wait, right? You may decide that even though the processor is not fully being utilized, you as a human being are worth more than the processor time. Whereas if it's a multi-million-dollar machine, you may decide to do something different, right? So what can you do, thinking of like something we talked about before, if CPU utilization was important to you, how would you decide on which process to run? What is your, can you think of one technique you will do to make the CPU fully utilized for your application, right? Utilization only means that CPU being used for your application, not for you and the kernel, right? How do you make sure that your process gets the most CPU? What is one thing you can do to make it such that your process will always get, the processor is being used for your application the longest? Does it make sense? Can you think of how you may achieve that? Yes.
You use this fuse system called as possible.
Yeah, few system calls, but system calls assume, let's assume CPU call, system call is still helping you, right? So so you consider the CPU used inside the CPU system call for your process should be charged to you, right? So consider a case where, so I don't want to switch between people, right? So one of the ways is, let's say there are two processes, right? If I have to switch from A to B, right, that switch is overhead. The switch's time is the dispatcher when it's running. That's not being processed for you, right? If I want to maximize the amount of time that is given to different process, I would not do context switches unless I have to, right? If you do I/O, there's something I can do, but I would not preempt you, right? I will let you run as much as you want, because if I have to do a context switch, I won't do any preemption, because if I have to, so if you give up your CPU, that's fine. But if you don't give up your CPU, if I have to yank you, I have to run the dispatcher, that's a waste, right? So if you go back to your clock example, if I want to optimize this stuff, I would make the clock frequency very small, right? Instead of 100 hertz, I'll make it 1 hertz, right? Every 1 second I interrupt to make sure that somebody switches over. I may even make it smaller, right? So I said every minute, I just check to see who's running. If you're still running, I give it to you kind of thing, right? So if I go this way, if I reduce the amount of time that I make a decision, then the dispatcher does not run at all. You keep running till how much CPU time you want, right? And that's one way you can achieve that, right? So the next goal is throughput, right? Which is defined as the number of processes which you can get through, right? It does not say anything about which is what. It just says number of processes, right? So it does not make any difference if you're talking about processes of all the same size. So if all processes need 10 seconds to run, right, the throughput metric doesn't make too much sense. But suppose you have 1,000 processes which need 1 second, and you have one which requires 1 hour, right? Throughput may decide which one to run, because if you run the smaller ones faster, you're getting a lot of the processes through the system, right? So you're only looking at how much time each of them, how much processes you're getting out of the system, right? So optimizing for throughput would mean that you're getting most of the processes out, which may mean that some of the longer running processes get left behind, but you don't care. You want to get the most of them out of the system, right? So that's one metric you can optimize for. The other time is the turnaround time. The time that it takes for you to execute a certain process, right? So if your process requires 10 seconds to run, turnaround time is trying to see how much time it actually took. So if it takes 10 seconds, if it only needed 10 seconds if there's no scheduling decisions, but turns out it needed 12 seconds. So that's the turnaround time. So you want to get the process in and out as quickly as possible, and that would be affected by the decision you might have made in the previous case, right? If you chose to keep the long-running processes waiting, then the turnaround time for it will keep going up. So you have to kind of balance, right? Does that make sense? Turnaround time, you're trying to see how what's the overall time it took. Waiting time, again, you can look at the amount of time it's sitting on the waiting queue, right? And you want to minimize the waiting time. You want to minimize the response time, right? Response time is another measure which makes sense on an interactive process. Response time says once you decide you want something, how soon do you get the processor to do your task, right? And you can notice it if you're typing on a keyboard. Response time is the time you say once you type a key, when it shows up on your word processing document or what have you, right? So the goal is to maximize some of these things and minimize some of these things. But these goals are contradictory. You can't have a process which does all of it at the same time, right? So for example, if you're trying to maximize the CPU utilization, that means I would not context switch. I don't want on the dispatcher. I'll let everyone finish whatever they're doing, which means that your response time would be horrible, right? It'll be good for somebody who's running. It'll be bad for the person who's left behind. So I have to balance all this stuff, and I can't clearly build an operating system which can do all of this, right? I have to figure out how much of it I want to do, and that's the problem of scheduling, right? Scheduling is a very simple task. The challenge is there are so many different reasons why you want to do the scheduling, and each one of those will make a system good or bad. And modern operating systems have multiple different schedulers running on the same system. Separate processes go through different kind of scheduler, but the reason is because of all this stuff, right? You may notice it because some of these processes are considered to be interactive, some of them are considered to be background processes, and you want them to be treated differently, and we'll see how you may do that in a little bit, right? The idea here is if I'm using a PowerPoint on this machine, right, I want very good response time. When I press this button, I want the next slide to come on immediately, right? And at this same time, the machine is doing something else. I mean, it's probably like looking at the background, to doing some cleaning or what have you. Right? It's running a virus checker, right? I don't want the virus checker to have very good response time. I want my PowerPoint to have instantaneous response time. The virus checker to operate in a different set of parameters because this machine is meant to be responding to me, right? Whereas if this is a mainframe, it's calculating your grades, it may do different stuff. It may not care if I move my mouse because it's doing something more important. So that's the challenge, right? So you need to understand what are the different ways you may organize, and you cannot say one is better than the other. It depends on what your goal was, what your machine is designed for, right? And this is one of the reasons why when you buy from Microsoft operating system, they have Microsoft Home, Premier, which I think is the same, right? But they can potentially make it different such that they can decide home users may care about responsiveness, corporate users may care about something else, and servers may care about something else. And server, they have different versions. If you look at the way they sell the operating system, right? Within the servers, they have normal server and then this super duper server kind of stuff, right? So they can charge you differently, but they also could do such that. So if you take a server, Microsoft server, right, and if you decide that okay, that costs so much more than what my laptop operating system does, so maybe that's a better operating system than my laptop operating system. So if you take the server operating system from Microsoft, which may look the same exact, in terms of the screen and stuff, and if you put that onto your laptop, right, you don't get a better operating system experience because it's optimized for something else, right? It may be optimized to say this is meant to be a server, so ignore all the mouse movements because you're meant to do something. So if you take a server operating system and put it on a laptop, you may find that it's really bad. And all that makes it bad or good is these decisions, which may not be that complicated, but may give you a totally different feel. Right? In the same way or the other way. If you take a laptop operating system and put it into a server, you may find that it's not doing what you expected it to do. Right? And so that's the magic that different companies do, because you can't build one operating system which can do anything and everything you can throw at it. Right? And so this is the stuff from the previous slide, the notion of what you want to be maximized, what you want to be minimized. And so the way you analyze this is through what is called a Gantt chart. The idea of Gantt chart is you sort of draw some representation like this, where you say when each process was running, right? So when you look at this graph, you can make some analysis, right? So for example, without looking at anything about the stuff above there, so this means that you had 3 processes, right? Starting at 0, right? Process 1 took 24, process 2 took 27, process 1 finished at 24, process 2 finished at 27, process 3 finished at 30, right? So for some way that you scheduled, this is how you ran the process. So regardless of what you did, you'll always finish at the 30th mark, but your particular way of scheduling meant that they got the CPU to run this way, and then you can look at that to figure out what's the response time, what's the wait time, and so on and so forth. So this is a good way to look at analysis, right? So the first schedule algorithm we look at is called first come first serve, right? It's a very simple process. So whoever comes to the ready queue, whoever comes first gets all they wanted. There's no preemption. There's no what have you. And then when you're done, the next person gets, and so on and so forth. Right? To understand analyze this program, you have to have a sequence of some way processes coming, so you can make some assumptions. So for example, in this case, there are 3 processes: P1, P2, P3. P1 requests 24 of CPU, and P2 requests 3, and P3 requests 3. Right? So those are known a priori, right? And you're trying to figure out what's the parameters for this particular schedule. And the order in which they arrive is P1, P2, P3, right? The order makes big difference because this is first come, first serve. So P1 came first, P2 came first, next, and the P3 came the last, right? So if that's the order they came, if it's first come, first serve, P1 came first, so it gets to run. P2 came next, it gets to run. P3 came, it gets to run. So overall time to run the whole thing is still 30. That's not going to be changed. But the waiting time, right? The waiting time for P1 is 0, because when it came, they all came at this instant, but in that order. So P1's waiting time is 0. P2's is 24, because it has to wait till this point to run. And P3's is 27, right? So the average waiting time, if you look at the average of those, is 17, right? Even though P0 had no waiting time, the average waiting time is 17. Okay? So now if you look at the same example, but you switch the order in which they arrive, right? If you instead of P1, P2, P3, now you have P2, P3, P1, right? It's the same every other way. They all finish at the same 30-second mark, right? But P2 gets run for its 3 seconds, and P3 gets run for its 3 seconds, and then you have the P1, right? So now if you look at the waiting time, P1 has to wait for 6 seconds before it gets to run. P2 has 0 wait time, P3 has 3, right? So if you look at the average waiting time, it's only 3, right? So in the previous case it was 17, in this case it's 3, right? So this is a way to analyze this particular schedule for whatever processes are coming. Because if you look at both the schedules, they both took 30 seconds of time, right? At the 30-second mark, in both the cases, all the processes are finished. In one case, the average waiting time is 17. The other case, average waiting time is 3, right? So if waiting time was your concern, first come, first serve would not be a good way to go, right? Depending on how the stuff, because the larger ones hog the CPU more than the smaller ones, right? And this is called a convoy effect, right? The short processes may fall behind a convoy, right? This is an effect you see on roads, right? If you're on a single lane road and you have instead of a long process, you look at a slow car, right? So you get on a single lane road, you have a slow car in the front and it's going at like 10 miles an hour, right? So all the sports cars are waiting for that one to clear up. So you create a convoy of these cars, and the bottleneck is the one in the front, which is slow, or in this case, it's the one which takes the longest amount of time, right? How would you fix the case of, so imagine a road with only one lane, right? How would you make the convoy effect fixed? How do you make the average speed of the road improve, right? You have one, like, let's say you have an 18-wheeler going very slow. You have a bunch of like sports cars in the back. How would you do that? Yes?
Let them pass the 18-wheelers somehow. Give them some method to do that.
So, yeah, you would let them pass, right? So one way to do that would be to do a preemption, right? You can preempt, you can do something, right? If there's no preemption, which is like sort of like you stopping the truck, right? There's not a whole lot you can do, right? If you're doing the first come first serve model, right? The first car which came into the road has to go first. Then you're kind of stuck. You're kind of going at the speed of the slowest car, right? So in these situations, the best way to do that is to do a preemption, where you kind of magically take the slow car out of the road, let the other two cars go, and then put it back, and then everybody goes. So that's called the convoy effect, and this is the Gantt chart that you use to analyze this system, right? So there are lots of different ways of scheduling these things, right? But remember, all these scheduling things are no magic. They're trying to optimize some stuff. The way they do the stuff, the way they implement the scheduling is not that complicated. The analysis of why you're doing this is the more interesting stuff, right? Is there a reason why you would not want to run a very complicated algorithm to figure out which process to run, right? The scheduler can, you can think of like a very complicated mechanism, right? First come, first serve is so trivial, right? Can you think of another complicated mechanism, and can you think of why you may not want to do that? Does it make sense to come up with a very complicated scheduling algorithm? Complicated meaning like it takes a lot of time to proceed. You want to guess why?
Just because like it'll increase the overhead. If you're scheduling them, it'll take
Yeah.
longer if it has to decide which one to take.
Yeah, exactly. So this is part of a dispatcher, right? So if it has to do lots of thinking, that's all overhead, right? And you want these things to happen very quickly, right? So if you're running this on the dispatcher, you want the decisions to be as simple as possible and get the most bang for the buck. The long-term scheduler can decide something. For the short-term scheduler, you want it to be as simple as possible. So you won't use any processes which are very complicated, right? And we'll see some of the algorithms which could potentially be complicated, but we'll try to simplify them, right? The next one, I'm just going to mention it here, we'll continue with the next class, is the shortest job first, right? If I knew the future, let's take the case of the cars, right? There are 3 cars come to the junction. One is 18-wheeler, and there are 2 cars. And suppose I knew that this 18-wheeler is not going to go more than 10 miles an hour, and the sports car can go at 100 miles an hour. If I knew this is what they're going to do on the future, right? Then I can run the shortest job or the fastest car first, right? Then I can avoid the convoy effect, right? This depends on me knowing the future. If I knew the future, then I may be able to do some things, right? And unfortunately, most operating systems don't know the future. So how do you approximate the future by looking at the past? Is some way to look at that. But essentially, the goals here is to try to be smarter rather than just blindly doing the first job which comes in first. You're trying to decide whether some are better than other ones for whatever metric you're choosing. Okay? If you're looking at time, I'm trying to see this one is going to use less time than the other one, so I'm going to choose one over the other. But just like in real life, right? 18-wheelers can go really fast, and a sports car can go really slow. So you make mistakes sometimes. But if you do it right, if you sort of predict the future, and the future is always happens that way, then you expect some things to happen, right? And we'll see why you again don't want to go wild and then do a very complicated algorithm to figure out the future. We try to do some things to make life a little bit better, right? We'll be continuing with this on the next class.